Hello, today we want to give explanations about fog computing. Let me introduce our group, comprises with me, Raphael Jedidiah, Falah Ramadan, and Rangga Rahmansyah. Today we want to give some explanation, perception, and example of fog computing. We hope you can finally understand about word of fog computing, drivers for fog, characteristic of fog, enabling technologies and prerequisites, and how they shape the way we access and distribute data. First, to understand fog computing, it is necessary to review the basic concept of cloud computing, right? Cloud computing represents a framework that grants users instant access to share a pool of computing resources over a network. These resources can be allocated and released quickly using a self-service approach. The main feature of the cloud computing model involves resource pooling, where workloads from multiple users or retainers are often placed on the same physical resource. And this ensures profitability and efficiency of the cloud computing model, thanks to economic of scale. Therefore, the use of computing and network virtualization technologies is an integral part of cloud computing. Cloud computing offers adaptive scalability features, allowing resources to be scaled up or down based on users' needs. Fog computing, commonly known as the fog, is a highly virtualized and distributed platform that integrates compute, storage, and networking services. The platform spans from IoT endpoints and gateways to the cloud data center, but primarily resides at the network edge. Fog serves as a complement to cloud computing, bringing its functionality closer to the point of data production, example, sensors, or where the data needs to be used, for example, like actuators. Rather than being an alternative to cloud computing, fog and cloud system work together, enabling the development of new categories and types of IoT applications that would not otherwise be possible. From the figure, we can see that the device domain is field or personal area network, right? It refers to the layer that encompasses the device and sensors at the edge of the network. These devices include IoT, sensors, actuators, gateways, and other endpoints devices that generate or consume data. For instance, sensor in smart homes collecting temperature data or motion sensors triggering local actions. And between the device domain and network domain, there's gateway. Gateways in field of the networks in computer systems act as entry points, facilitating connections between different networks or devices. It acts as an intermediary that enables communication, traffic management, and data flow control between different networks that may operate under different protocol standards. And in the network domain, it comprises of access of or aggregation and the core. The network domain, on the other hand, refers to the layer responsible for communication, transmission, and connectivity between the device domain and higher layers in the fog computing infrastructure. The access layer is the closest to the end user's devices such as computers, printers, phone, or other network endpoints. Its primary function is to provide network access to this device, typically through the switches or wireless access points. This layer is responsible for providing connectivity, ensuring end user devices can connect to the network efficiently and securely. And the aggregation layer sits between the access layer and the core layer and acts as an intermediary layer. It aggregates traffic from multiple access switches and then forward this aggregated traffic to the core layer. It can perform functions such as routing, implementing security measures, and providing connectivity between different parts of the network. And the core layer is the backbone of the network. It is designed to carry high speed, high volume traffic. Its main function is to convert and route data between different parts of network efficiently without doing extensive processing or causing delays. In this class, speed and reliability and minimal latency are essential. High-speed routers and switches are often used at the core layer to facilitate a rapid data transfer. The cloud domain consists of large-scale, centralized data centers that store, process, and manage vast amounts of data. For instance, like local networking devices like servers, routers, switches, and gateways that manage the flow of data between IoT devices and higher layers of the VoC infrastructure. The user domains concern the end user or consumers who interact with IT services like application and data. Users access data and services provided by both fog and cloud domains, interacting with application and systems designed to meet their needs. There are several IoT requirements that act as drivers for the fog architecture. There are data deluge, rapid mobility, reliable control, and data management analytics. First, we're gonna discuss about data deluge. It has been asserted that the total data generated from the beginning of human history until 2003 amounted to 5 exabytes. Presently, this vast amount of data is produced every 2 days, and this rate is steadily increasing. The anticipated connection of billions of devices to the network will further compound the challenge of managing this overwhelming volume data. At the crux of the issues lies the question of whether the technological advancements will progress swiftly enough to cope with the imminent surge in data. The technological evolution curves are prominent. One traces the evolution of computing and storage technologies based on Moore's law, which dictates a doubling in capability or capacity every 18 months. The other reflects bandwidth growth at the edge of the network driven by the Nelson's law, which predicts bandwidth will double every 24 months. Given the correlation between developments in computing and storage technologies and the expansion of data volumes, it is conceivably that the future IoT could see that created with a speed far exceeds the network's ability to transport information from the edge, where it is generated by countless devices to the cloud, where it must ultimately be processed and potentially stored. This gap between data volume and available bandwidth can be compared to trying to push a golf ball through a straw. Fortunately, Moore's law not only solves part of the problem but also provides an important solution. It can be leveraged to improve the network by integrating compute and storage capabilities at the edge. This allows the network to perform data processing, analysis, and storage locally instead of just sending all the data to the cloud. So cloud computing becomes fog computing when brought closer to data sources, IoT devices. This shift has led to emergence of fog computing, where processing and storage takes place closer to the origin of data, thereby reducing pressure on the network and improving efficiency. The second one is rapid mobility. Some IoT applications require support for rapid movement of devices, such as sensors on moving vehicles that communicate with road infrastructure or vehicle passengers. Rapid mobility can cause network fluctuations due to signal issues, leading to service degradation or intermittent loss of cloud connectivity. Bandwidth limitation and latency in the communication path to the cloud can impact IoT operation. Manufacturers, including radio coverage, interference, and shared resources among mobile nodes, contribute to these characteristics. To ensure the required quality of services and reliability, especially for mobile devices covering long distances, the cloud infrastructure must integrate mobile computing and storage capabilities. And these mobile capabilities can be physically integrated into the device or virtually observe and track the device at the edge of the network. In doing so, fog computing complements the cloud, ensuring the essential ubiquity and reliability needed for rapid mobility in IoT. The third one is reliable control. IoT applications emphasizing closed-loop control and actuation commonly exhibit specific traits, like the data input and processing logic needed for control decision demand extensive computation and substantial storage. The devices used for sensing actuation are usually constrained and, as a result, require external systems or infrastructure to manage storage and computing functions. Many of these control applications necessitate a very low latency for accurate operation. In certain situations, connecting to the cloud might either be too costly or unreliable due to rapid mobility. These combined characteristics make relying on cloud computing unsuitable for ensuring reliable real-time control with consistent latency. This is where fog computing can complement the cloud to meet these specialized IoT application needs. The fourth one is data management and analytics. The IoT applications category is characterized by large-scale convergence, involving large numbers of data generating devices, while geographical distribution of this data, large volumes of data required to collect, aggregation, processing, and accessibility for real-time analysis or closed-loop operation. For this application, a data management and analytics platform capable of meeting performance and scalability requirements is essential. Experience gained with large number information and communication system has shown that distributed hierarchical systems provide the necessary flexibility while also meeting important performance criteria. These systems often leverage data proximity for core functions, minimizing the need for remote data access in critical functions. Interaction between widely distributed entities primarily involves system-wide functions. This operating model is especially suited to data management and analytics in the IT context, where data at the edge of the network has importance and relevance, often losing relevance as it sinks deeper. Considering the ambient noise sensor in smart city application, which continuously measures noise level and transmits the recorded data. Transmitting all the data to the cloud is unnecessary and inefficient compared to the alternative design, a local analysis function near the sensor that filters reading based on the predefined threshold, sending only relevant readings to the cloud above the threshold to the cloud, such as alerts to city staff. Fog computing combined with cloud computing provides the essential computing and storage infrastructure required to support the analysis and management of such hierarchical and data. Both the fog and the cloud consist of three fundamental components: computing, storage, and networking. Nevertheless, from the slide, we can see distinct features differentiate the fog from the cloud, like the latency and jitter. For cloud computing, it has medium until high latency or jitter, rather than fog computing. And the location of servers of cloud computing is within the internet, but fog computing is network edge. And the distance between data sources and consumers for cloud computing is multiple hosts, but for computing is single host. And the only one that has location awareness is only for computing. And for geo distribution for cloud computing is centralized, but for computing is distributed. A number of nodes for cloud computing is very large, but for computing is larger than that. Support for mobility, for computing um, that have the support for mobility. And the data analytics for cloud computing is data at rest, but the fog computing is data in motion. And the connectivity of cloud computing is wireline, and the connectivity of computing is wireless. If we can summarize, the differences are proximity and latency. Fog locates services close to the data source and users, leveraging location awareness and low latency to process and reach data. And for geographical and architectural distribution, unlike the centralized cloud model, fog works with distributed architecture across different locations. Node count and scale. While cloud requires a large scale data centers, fog offers scalability even higher node counts. And for mobility, fog nodes and resources, including data sources, consumers, and compute or storage are mobile. And for real-time processing, fog emphasizes real-time analysis of streaming data instead of batch processing, focusing on data in motion rather than data at rest. And for wireless connectivity, unlike the cloud's reliance on wired technologies such as Gigabit Ethernet, fog primarily uses wireless links, supporting mobility and convenience. And for resource heterogeneity, cloud data centers deploy homogeneous resources to support operation, while fog, which is federated across different entities, uses different resources different in capacity, form, and operating environment. And we are moving to enabling technologies and prerequisite. Making the vision of fog computing a reality requires specific technologies that act as the building blocks and are essential for its architecture. These include lightweight compute virtualization, network mobility, orchestration, and application enablement technologies. Let's dive into detailed discussion about each of these technologies in the upcoming session. For the virtualization technologies, there are containers and virtual machines, Docker, application mobility. And for network support for mobility, there are AVPN and LISP. And for orchestration, there are topology, things connectivity, network performance guarantees, and for data management, There are data in motion and search technologies and engines. First, I want to discuss about visualization technologies. The essence of fog computing lies in locating computing functions close to where data is generated or consumed. It depends on lightweight compute visualization technologies to configure workloads on fog nodes, which act as shared computing resources for various IoT applications. Virtualization technologies consolidate or divide computer resources, forming one or more operating environments using methods such as hardware and software partitioning, hardware emulation, and resource sharing. Virtualization offers many benefits. It unifies hardware and application, reducing costs associated with underutilized infrastructure. It also provides a secure execution environment for application and the flexibility to run multiple operating systems on the same hardware. It facilitates software stack migration and application packaging, allowing easy migration between different hardware or application. At the hardware level, virtualization consists of hypervisor placed on top of physical hardware, creating virtual machines or VMs that can run a variety of operating systems. The application in these virtual machines are unaware of the underlying visualization. And I'm going to discuss about containers and virtual machines. As you can see from the slide, we can build virtual machine. We start off with the hardware such as server. And then on top of the hardware, there is a software called hypervisor. A hypervisor allows one machine to run multiple virtual machines. It's what allocates and controls the sharing of machine hardware. Some common hypervisors are VMware ESXi, Citrix Handler, and Microsoft Hyper-V. And on the top of the hypervisor are the virtual machine, and each if these will have their own operating system such as Windows, Linux, and Unix. After that, on the top of the operating system, there's the application that these machines are going to be running. So just like VMs, to create containers, we start off with the hardware such as server. And then on top of the hardware is an operating system such as Linux. Now instead of a hypervisor, containers will use a container engine. A container engine is what unpacks the container files and then hands them off to the core of the operating system, which is the kernel. The major difference between containers and virtual machine is that each VM contains an entire operating system, which makes their file size larger, which is why they are slower to boot up. But on the other hand, containers don't. The containers share the underlying operating systems that on the server between them. Containers only contain one application, which makes their file size much smaller, and this is why containers are considered lightweight, which also make them lightning fast. So while VMs can take minutes to boot up, containers take milliseconds. Containers also consume less RAM and CPU power from the server than VMs. In the world of cloud computing, there are two big players, containers and virtual machine, like we discussed before. Both have strengths and weaknesses. Virtual machines, commonly known as VMs, operate at hardware or a deeper level, essentially mimicking an entire computer system with its own operating system, software, and drivers. Containers, on the other hand, operate at higher level, sharing the operating system and necessary libraries. They contain only what is important to run an application, making them much lighter than virtual machines in the term of processing and memory requirements. Containers hold a real edge over VMs when it comes to scaling up, not just in cloud computing, but also on fog. Their small memory requirement allows them to swiftly move between different nodes, making them super agile for rapid mobility. But there's a catch. Since containers share the same underlying operating system, they're not our go-to choice for developing apps that need a different operating system or version on the same hardware. VMs, on the other hand, have their own operating system copies, so they're versatile in that aspect. However, here's the deal. The shared operating system in containers can pose security risks, as a misbehaving code in one container should affect others on the same system. VMs having independent operating system, right, offer better solution between the application, resulting reduced security threats compared to containers.
Training the PPT. So uh, first, I want to explain about the identify versus location addresses with application mobility. Identity addresses serve as a unique identifier for mobile application or device, allowing them to be recognized regardless of their physical location within the network. This characteristic ensures seamless handover between different network segments, enabling application to maintain uninterrupted uh, as they move across various access points. Identify addresses play a significant role in scenarios where continuous interaction is essential, such as in VIP calls or online gaming, ensuring that the application can seamlessly switch network without interruption. On the other hand, location address indicate the specific network location of a mobile application, changing as the application moves between different subnets or access points. The management of location addresses is vital for tasks like load balancing, optimizing resource usage, ensuring security, and implementing access control mechanism by balancing the use of identity and location address effectively. Mobile application can maintain their unique identity while adapting to diverse network and environment, guaranteeing smooth operation and secure interaction. As we can see in the picture, that the location address, there are two location address different, and its mobility is connecting each other for each the location address. Um, uh, this mobility enables it to be, how do I say it, is make it more faster and more efficient. And then the next slide, the EVPN architecture. The EVPN or Ethernet Virtual Private Network is a network technology that provides layer 2 and layer 3 connectivity service over an IP or MPLS. MPLS is multi-protocol label switching. VPN allows different sites within a network to communicate with each other as if they were on the same local network, regardless of their physical location. The VPN architecture involves several key components and concepts. The first is PE or provider edge device. These are the routers or switch at the edge of the service provider network. PE are responsible for connecting customer network and exchanging EVPN routes. The second is CE or customer edge. These are the devices at the customer uh, premise, such as router or switches, that connect to the service provider PE device. And the third is EVE, or we can say is Ethernet VPN instance. Each VPN network consists of one or more EVEs, which are essentially isolated routing and forwarding tables. Each EVI represents a separate virtual network segment. And the fourth is MAC address. EVPN use MAC address learning to understand which devices are connected to which network segments. MAC address are learned to dynamically insert among PE devices using MPBGP or multi-protocol BGP to maintain a MAC to IP address mapping table. And the next is BGP or Border Gateway Protocol. EVPN use BGP as the control plane protocol to exchange MAC and IP address information between PE devices. BGP is extended to carry EVPN specific routes. And the next is also important. It is a type 2 and type 5 routes. EVPN defines different types of routes. Type 2 routes are used for the MAC address reachability information, while type 5 routes are used for IP traffic reachability information. EVPN architecture allow for efficient and flexible layer 2 and layer 3 connectivity between geographically disparate sites. It is commonly used in data centers, service provider network, and large enterprise network where seamless communication and mobility of virtual machine and device are essential. And as I already explained, and I will be now explaining in the terms of the in the picture. So there are four PE in the picture: PE1, PE3, PE2, and PE4. The PE1 is connected to the PE2, PE3, and PE4 through the MPLS, and the CE is connect to PE1 and PE2, while the CE is connect to PE3 and PE4, and their CE is connected by the MSC that they are defining as the MSC address and IP address. It is the root in the C1 is at root 2, and in the C3 is root 5. So it's the architecture of the EVPN, or Eternal Virtual Private Network. Next, I will be explaining about the mobility in EVPN. In EVPN, or Ethernet Virtual Private Network, mobility refers to the network ability to handle device moving within the network without losing connectivity or disrupting service. EVPN provides a vision solution for both MAC, or media access control, and IP mobility in Ethernet network. For MAC mobility, EVPN use type 2 routes to advertise address when a device moves to a new location. EVPN updates the type 2 routes, ensuring that the other device in the network can reach the moving device at its new location. This allows for seamless communication, even if devices change their physical attachment point within the network. Additionally, EVPN supports IP mobility through Type 5 route. When a device moves to a different IP subnet, VPN updates the Type 5 route to reflect the device new location. This means that device can maintain the IP address across different subnets, and is allowing for uninterrupted communication and ensuring that service remain accessible regardless of the device physical location. And as we can see in the picture, uh, this is the mobility is a perfect mobility for the EVPN. So it makes the EVPN so flexible in mobility. So the CE1 is connect to the P origin, and it's connect to the P target through the CE1, connect to the CE3, and the P origin is connect it to the PE2, PE4, and the target. And the P origin advanced MIC routes for M1 and IP1, and VM-M1 move the CE1 to CE3 location, and PE2 or P4 install M1 route towards PE origin, as we can see in the picture. And after VM sends traffic at new location, PE target now advertise MIC routes for M1 with spatial mobility attribute. And the last one, PE origin withdraws its M1 route and install a new one pointing to PE target. So by the explanation, it can be concluded that it makes the mobility of EVPN perfect. So let's go to the next slide. Default IP gateway problem with VM mobility. The default IP gateway problem with VM or virtual machine mobility occurs when a virtual machine is moved or migrated to a different network or subnet, and its default IP gateway, which provides a route to other network, becomes invalid or inaccessible in the new location. This situation can lead to network connectivity issues for the virtual machine. When a virtual machine is powered on, it typically obtains its network configuration, including the default gateway from a DHCP, our Dynamic Host Configuration Protocol, server or through manual configuration. If the virtual machine is moved to a different network segment or subnet, the previously configured default gateway might not be valid in the new location. As a result, the virtual machine cannot communicate with device outside its subnet because it lacks a valid route through the connect default gateway. This leads to a network isolation, making it impossible for the virtual machine to access resources on other subnets on the internet. Solving the default IP gateway problem with VM or virtual machine mobility requires appropriate network configuration adjustment. And it can be solved with several ways. The first is configure the dynamic routing protocol. By implementing the dynamic route protocol like OSPF or Open Shortest Path First or BGP Border Gateway Protocol in the network infrastructure, this protocol automatically updates routing table including device default gateway information when virtual machine move to different subnets. And the next is utilize VLAN or virtual local area network. A group virtual machine into VLAN based on their mobility requirement. VLAN can segregate and export traffic logically, allowing for easier management of default gateway within specific VLAN. And the next is implement software-defined networking or SDN. SDN technologies enable centralized management of network configuration, including default gateway assignment. SDN controllers can dynamically adjust routing information based on VM mobility events. And the next is utilize IP address management or IPAM. IPAM tools can automate IP address assignment and default gateway configuration based on the VM location. This tool helps ensure that the correct default gateway is assigned when a VM is moved. And the next is update the DHCP server configuration. Configure the DHCP server to provide the correct default gateway information based on the VM subnet or VLAN. DHCP server policies can be adjusted dynamically to accommodate VM mobility. And by implementing these strategies, administrator can mitigate the default IP gateway problem with VM mobility, ensuring that the virtual machine maintains seamless network connectivity even when they are moved or migrated to different locations within the network. And the EVPN default gateway solution, because previously I explained about the problem. Now I can explain about the solution to fix the previous problem. The EVPN default gateway solution address the challenge of maintaining seamless network connectivity, especially in the context of virtual machine. This solution employs integrated routing and bridge or IRB, allowing device to act both as a layer 2 switch for Ethernet frame within the same VLAN as layer 2 routes for IP packets anycase gateway, a technique where multiple routes share the IP address. Ensure efficient routing by directing packet to the nearest router with the anycase IP address, reducing latency. Active multi-homing enable device to have redundant connection to different routers, each sharing the same anycase gateway IP. In this setup, EVPN type 5 routes are used to distribute information about the anycase gateway IP address across the network. So as we can see in the picture, so there are 3 servers in the picture. The server 1 or the default is connect to the server 3. And the server 2 is connect to server 3 also, and it used the VM mobility to connect it to the server. And by using this method, as I already explained before, this will fix the problem of the default IP gateway problems. And the next is I will explain about the LISP architecture. LISP or Locator ID separation protocol is a network architecture that separates the device identity from its location in the network. In the LISP architecture, devices are assigned endpoint identifiers as their identities, and routing locators or RLOC represent their location in the network. This separation allows for more efficient and scalable routing and addressing on the internet. When a device wants to communicate with another, it uses its AID to initiate the connection. The mapping system in LISP translates the AID to the corresponding RLOC, allowing the data packet to be routed to the correct location efficiently. LISP is particularly beneficial in scenarios where devices frequently change their network location or need to roam across different networks, as it enables seamless connectivity without the need for remembering IP address. By decoupling identity and location, LISP enhances the network scalability, flexibility, and mobility, making it a valuable solution in modern network architecture. So, as we can see in the picture, the RLD expand. This is the implementation uh, of the what I have explained before. This system in this the mapping server and the map resolver and it's connect to here, and here. So yeah. And the next slide will be represented by my friend Rangga.
Okay, welcome everyone. Today we're delving into the fascinating world of the LISP via mobility, also known as LISP Force Mobility. This technology enables an host to move across the different subnets or extended subnets to a different location while retaining their original IP address. In the next slide, in this slide, we're gonna talk and we'll explore the intricacies of the LSIP via mobility. So, LSIP via mobility stands for Locator or ID Separation Protocol via mobility. It revolutionized the way IP addresses are managed and allows for seamless host mobility. And LSIP via mobility supports two primary types of host mobility. Across subnet. The first one is the across subnet, when an end host moves to a completely different subnet while keeping its original IP address. The next one is the extended subnet, where an end host extends its subnet to a different location and still maintaining its original IP address. So, we're gonna talk about the extended subnet mode first. In the end host carries its layer 3 address to the remote site. Importantly, the prefix of the IP address remains the same as the remote site. This mode requires a layer 2 LAN extension to ensure a seamless communication between the host and its original subnet. So, for the across subnet modes, the end host carries a different network prefix when it moves to the remote site. This means that the IP address is no longer part of the original subnet. In this case, a layer 2 extension is not needed between sites, making it more a flexible option. Uh, LISP via mobility magic lies in its ability to provide seamless IP mobility. When a host moves to the mapping system, ensure that its original IP address remains reachable, regardless of the chosen mobility model. In the extended subnet mode, a layer 2 LAN extension is required to bridge the end host with original subnet. This extension ensures the host can maintain a communication using its existing IP address. So, the benefit of the LISP via mobility offers a numerous advantages, like enhanced host mobility, where the host can move freely across subnets or extend their subnet without disrupting connectivity. And also the scalability, it efficient handles a growing number of mobile hosts, more than a flexible network design that choose between the across subnet and extended subnet modes allow for a tailored network solution. Okay, for the use case, in the LISP via mobility finds application in various scenario like data centers, efficient load balancings and failover enterprise, seamless host mobility for employees, cloud environments, scalable virtual machine like VM mobility, and this is the real world adoption. It's like the organization are recognizing the power of this LISP VM mobility, and it's increasingly being adopted in real-world network deployment. In conclusion, the LSIP VM mobility is a transformative technology that redefines the how IP address and hosts move within the networks. It offers two mobility modes across subnet and the extended subnet, each with distinct advantages. The use of the layer 2 LAN extension or the absence thereof in this mode provide a flexibility in network design. With its real-world application and a growing adoption, LSIP VM mobility is a key player in the world of the the world of the host mobility. Okay, for the next slide, let's break down the concept of the fog orchestration into a step-by-step explanation. Okay, in here, as we see, there's a cloud, fog orchestration, fog, and the things. The cloud, as we all know, in the backbone of the modern computing, it provides the infrastructure and service that enable data storage, processing, and the accessibility from anywhere in the world. So, below the cloud, we have the fog or edge layer. This is the layer where the data processing occurs to the source, reducing the latency and enabling the real-time decision making. And the fog layer is the bridge between the cloud and things in the Internet of Things, or IoT. As you can see, the things or in IoT refer in the countless devices and sensors that collect and transmit data. This can be anything from the thermostats and wearables transmit data, wearables to industrial sensors or autonomous vehicles. In the first step in the fog orchestration is the fog resource discovery. This involves the identifying the and cataloging the various resources in the fog layer, such as edge servers, gateways, and other edge devices. And the next is the cloud and fog integration. Once resources in the fog layer are discovered, the next step is integrate this fog resource with the cloud, and this integration ensures that data can seamlessly flow between the fog layer and the cloud. So, within the cloud and the fog integrated, the orchestration process includes IoT device onboarding. This step involves the registering and configuring IoT device, making them the part of the orchestrated network. So, once the IoT devices are part of the network, the fog orchestration facilitates real-time data processing. This means that the data generated by the IoT device can be real-time data processing. This means that the data generated by IoT device can be processed at the fog layer, reducing the latency and enable quicker response. So, with real-time data processing in place, the fog layer becomes a hub for intelligent decision making. Algorithm and rules can be applied to the data, enabling autonomous action and alerts. The benefits of the orchestrations are really numerous, like including reduced latency, like we were, enhanced security, and improve operational efficiency. Use case span is like various industries from smart city to the industrial automation and maybe beyond of that. Okay, In conclusion, the fog orchestration plays a crucial role in bringing the cloud and the fog layer. An IoT device orchestrates the entire process from the resource recovery to a real-time data processing, enabling intelligent decision making as the IoT ecosystems continues to expand. Fox orchestrants will become increasingly vital in ensuring efficient and responsive operation. Okay, from this we can see as an example of this Fox orchestration in multi-user business process. Across every industry and line of business, like the first one is there is a financial service. Next is public sector education non-provide, professional service, retails, sales, service, human resource, and IT. So in here we can see like many things that we can do with this Fox orchestration to make it more efficiency for us to do things. Okay, so the example use case of the example use case for this is, I take it like the return merchandise authorization, or maybe we can call it RMA. And here, we can see we divide into perspective. The first one is the customer experience and the service team experience. In the first step, we can initiate the RMA, where in the service team we can see that the lookup customer data and classify the root case and goes to the agent to check the warranty and the entitlements, where the service team is gonna be checking the single pane for the customer data and auto validate the warranty and the entitlements to initiate the swarm. And for that goes to the approver, where the submit exception approvals gonna be in the service team. They're gonna check they're gonna be an auto root approval request, and when the auto update case once approved, in the customer experience they're gonna see the auto status updates. And for that, they're gonna be creating the create work order, where the autocomplete the WO intelligently recommended and replacement the parts. And goes to the third party repair, where the scheduled repair gonna be scheduled using the service team, where the auto schedule technician and optimize the route. And in the customer, they're gonna seeing the auto notification to schedule the via portal or maybe the chatbot. To fulfillment manager, where the execute on-site repair. In the service team is gonna be the customer details are in the mobile app and the auto checklist to ensure the accuracy of the data. And again, in the customer experience, they're gonna be seeing the real-time tracking of the technician and route. So they're gonna seeing the real-time data about what's in the repairman's gonna do. Goes to the field tag, where the generated complete work order are auto, and we can see to the RMA fulfill, where the customer gonna sing the personalized marketing email for them. Oh, so it's like that for the Fox orchestrates use case for this maybe. Okay, next to the slide, where we can see the data management. In here we have the DIKW pyramid. This is also known the unraveling the hierarchy of the knowledge. So, let's commence by understanding the core concept of the DIKW pyramid. At the base of the pyramid, we find data. Data is defined as a symbol that represents the properties of objects, even a specific condition. It is the product of the observation by like meanings without processing. In essence, data merely signifies in its own existence. So moving up to the next level, we encounter the information. Information is a more comprehensive representation than data. It is data refined with description contextual relevance, analytical purpose, and analytical methods. Information add meanings to raw data from before. So, knowledge emerges from accumulated information over time. It is the bridge that allows a transformation from information to instruction. Knowledge can be obtained through a sharing and instruction from others. Furthermore, knowledge is often defined as a collection of valuable information. At the apex of the DIKW pyramid, we find a wisdom. To reach this level, one must ponder questions such as why should something be done and what is the best course of action. In essence, wisdom represents knowledge that has been applied in practical application and decision. So, how can we apply this framework to our real world? From data to information, the transformation from data to information involves adding context, analytical methods, and purpose to raw data, making it more meaningful. So, and then from the information to knowledge, there's an accumulation and assimilation data and information over time, enabling individuals to apply this understanding. For then the knowledge to wisdom. The wisdom is achieved by applying knowledge to a real life situation and making informed decision. It represents the practical embodiment of accumulated wisdom. Wisdom is a powerful tool, particularly in decision making and quest for the best course of action. It signifies the pinnacle of human understanding. So in conclusion, the DIKW pyramids offer a structured perspective on the hierarchy of knowledge. From data to wisdom, these frameworks remind us from the value in transforming raw data in practical wisdom, which in turn empowers better decision making in our increasingly data-driven world. Okay, in data management, let's begin by understanding the landscape of data management. In the focus on how it interplays with different layers of the network. This is included from the page before. So we can see the cloud data exposure. In the cloud, data exposure is managed through the standard application APIs using common data formats or ontology. Analysis is the key component as data from various sources is consolidated and processed. Okay, so in the network core, streamline data within the network core. Data over the core is greatly reduced, ensuring efficient data flow without unnecessary overhead. In a network with many fork nodes, data is in constant motion. To manage this, predicate and filters are applied to shift through relevant data. Contextual and dimensional data is considered. And aggregation and compression are employed to optimize data processing. Technique like pattern matching and categorization, classification, driven data handling. Next is the Internet of Things, or IoT, add another layer to the data management puzzle, where the IoT device requires protocol mediation to ensure seamless communication. Proxy authentication is vital for this secure data collection and context awareness, including location data. It is integrated into the mix. And now let's delve deeper into the challenge and solution in data management within the fog. Challenge 1: data overload. Managing data overload in the fog is major hurdle. Effective data filtering, aggregation, and compression techniques are employed to address this challenge. Then the challenge number 2 is the real-time processing, where real-time processing is essential to application in the fog. Pattern matching and categorization or classification techniques enable timely analysis and decision making. The challenge number 3 is the security. Security remains a top priority. Of course, the proxy authentication and secure data collection method safeguard data during its journey from IT device to the cloud. So for that, we're gonna have the fog data management solution, where the fog data management solution encompass a blend of technique, including a context awareness, ontology-based data formats, and well-defined API. This solution aims to streamline data management and analysis within the fog. In conclusion, data management in the fog is a multi-phase challenge that demands creative solutions to successfully navigate this landscape. And we must employ technique like filtering, aggregation, real-time processing, robust the employ technique like filtering, robust the security measures, as the fog continues to play a pivotal role in the data management, adapting to its unique characteristic to become increasingly vital. And lastly, for the data search in fog, let's begin by understanding the intricacy of data search within the fog. The first, there's the fog nodes, are at the heart of the data search in the fog. These nodes act as the intermediaries between each device and the cloud, facilitating data processing and storage at the network edge. Federation Message Bus. The Federation Message Bus serve as a crucial communication backbone. It allows fog nodes to exchange information and query data efficiently across the fog network. And the concept of the search radius is fundamental. It defines the geographical area or range within which data searches are conducted. Queries, on the other hand, are the specific requests for data within the radius, and efficient data retrieval. The combination of fog nodes, the Federation's message bus, search radius, and queries ensure efficient data retrieval. Data can be located, processed, and delivered with minimal latency and network congestion. Real-world application data search in the fog is integral to the various real-world application, from smart city industrial automation. This technology streamlines data retrieval and analysis, enabling smarter decision making. In conclusion, the data search in the fog leverage fog nodes, Federation message bus, search radius, and queries to facilitate the efficient data retrieval and analysis. This technology is central to the ever-expanding Internet of Things or IoT and Fox computing landscape. Uh, Maybe that's all from us. Thank you for the time for us to do the this task. Maybe that's all from us. Sorry if there anything's wrong from us, and that's it from us. Thank you.